Hi guys, welcome to my channel. Imagine you are managing a large portfolio. You have hundreds of stocks, and for each stock, you have dozens of variables: interest rates, inflation, GDP growth, credit spread. At first, this sounds like an advantage. More information should mean better analysis. But here's the problem: many of these variables are moving together. Interest rates and bond yields, different measure of inflation, different equity market index, different measure of economic growth. So you might think you have 100 different sorts of information, when in reality many of them are telling you essentially the same story. This creates a problem for analysts. The database becomes large, complicated, and difficult to interpret. And this is where principal component analysis, or PCA, become extremely useful. PCA asks a powerful question: can we check a large number of correlated variables and summarize more of their information using a much smaller number of independent components? That's the idea we build today. Before we get to PCA, we need to understand where it fits. Machine learning can properly be divided into supervised and unsupervised learning. In supervised learning, we have target variable. For example, will this company default? Will this stock outperform? What will revenue be next year? The model learns the relationship between input and unknown outcome. Unsupervised learning is different. There is no predefined target variable. Instead, we asking what structure exists inside this data. We might want to identify groups, patterns, or underlying dimensions, and PCA is one of the most important tools for doing exactly that. So let's start with the problem PCA is designed to solve. Suppose we have a dataset containing 100 variables. If those variables were completely unrelated, we might generally have 100 distinct pieces of information, but that's often not what happens. Financial variables tend to be correlated. For example, several different economic indicators may move together because they are responding to the same underlying economic force. So we have a lot of variables, but much less unique information than the number of variables suggests. This creates what's called high-dimensional data set. And high-dimensional data can be difficult to analyze, visualize, and model. PCA provides a way to compress that information. Here's the central idea. PCA takes a large number of potentially correlated variables and transform them into a smaller number of principal components. These principal components are new variables, but they are not simply individual variables from the original data set. Each principal component is a linear combination of the original variable. Think about it this way. Suppose you have 10 economic indicators. Instead of analyzing on 10 separately, PCA might construct a new component that capture the dominant pattern shared by those indicators. That becomes principal component 1. Then PCA finds another component that capture another important dimensions of variations. That's principal component 2, and so on. The result is a much smaller set of variables that can summarize much of the information contained in the original dataset. Each principal component is associated with an age vector. The agent vector tells us the way used to construct that principal component from the original variables. So conceptually, principal component 1 equals a weighted combinations of the original variable. The weight comes from the agent vectors. Then we have the agent's value. The agent value tells us how much the total variance in the dataset is explained by that principal component, and this is extremely important. A large eigenvalue means the component explains more of the variance of the original data. So PCA ranks the principal components according to the amount of the variance they explain. Typically, PC1 explains the mode, PC2 explains the next mode, then PC3, PC4, and so on. The explanatory power generally declines as we move through the component. So let's make this concrete. Suppose we start with 10 variables. PCA tells us principal component 1 explains 50% of the total variance. Principal component 2 explains another 20%. Principal component 3 explains another 10%. Now we capture 80% of the variations in the original 10 variables using only 3 components. That's the power of dimensionality reductions. We went from 10 variables to 3, while retaining most of the information. The exact number will depend on the data set, but the institutions is what matters. PCA trades some information for simplicity, and analysts has to decide how much information they are willing to sacrifice. This leads to one of the most important practical questions: how many principal components should we keep? If we keep only 1 or 2 components, the dataset becomes extremely simple, but we may throw away too much information. If we keep on the components, we retain all the information, but we gain very little from dimensionality reductions. So there is a trade-off. We want a small number of components that explain a sufficiently large proportion of the total variance. In practice, a common rule of thumb is to retain enough principal components to explain roughly 85 to 95% of the total variance. The exact threshold is not a universal law, it's a practical decision. The analyst is balancing simplicity against information retentions. This is the major disadvantage of PCA. The principal components are combinations of the original variable, so they can be difficult to interpret economically. In my principal components, it constructs from 30% GDP growth, 25% interest rates, 20% inflation, 15% credit spread, and several other variables. What exactly is that components? It is economic growth, monetary policies, financial conditions, maybe some combinations of all 3. That's the problem. PCA is excellent at compressing information, but it is not necessarily excellent at giving that information an intuitive economic label. This is why PCA is sometimes described as relatively black box like from the user perspective. Less complexity, but potentially less interpretability. Thanks for watching.